Hello, physics students. This is a video about the last part of chapter 11, which is chapter 11 is all about momentum and impulse, the conservation of momentum, collisions, things like that. So this last part, talking about first, I want to talk about an explosion. So a collision is when multiple objects come together and meet, and then they might stick together, or they might bounce off one another. But an explosion is kind of the opposite of that. It's where you have one object that then explodes, so it turns into multiple objects that then fly apart. But it's still the same situation as far as momentum is concerned and its conservation. Particles first have a brief intense interaction, then they move apart from each other. The explosive forces are internal forces. If the system is isolated, its total momentum during the explosion will be conserved. So an example of that, this should probably help us more than anything is doing an example. All right, recoil. A 10-gram bullet is fired from a 3-kilogram rifle with a speed of 500 meters per second. What is the recoil speed of the rifle? All right, you might not think about this as an explosion, but it is. It's the bullet and the rifle are together. They're one thing, at least as far as physics might consider it. And then a brief interaction happens where the bullet powder explodes. It causes a explosion or a fire or whatever, and that sends the bullet away. So then that is an explosion, because they have those that were one thing have now become two things, and they're going in different directions. All right, so if you've ever shot a gun before, you know, especially like a rifle or a shotgun, you can feel the gun itself after you fire recoil against your shoulder. So it has a certain momentum going the opposite direction of where the way that the bullet's going. So that's what we're going to do. So first of all, let's just say the initial momentum equals the final momentum. What is the initial momentum of the system? So you got the bullet and the gun is one thing. Once the system is the bullet and the gun, what is its initial momentum? Its initial momentum is its mass times its velocity, but its velocity is 0 at the beginning. So the initial momentum is 0. The final momentum, we now have two separate momenta in the final situation. So we have the momentum of the bullet. The momentum of the bullet is its mass times velocity. Its mass is 10 grams, so I'm going to say 0.01 kilograms, and its velocity is 500 meters per second. Plus the momentum of the rifle, which was, its mass is 3 kilograms, and its velocity is what we're looking for, the velocity of the rifle. So this is going to be a pretty simple algebra problem here. So that's 5 plus 3 VR, subtract 5 from both sides, divided by 3, and we have VR by itself. Negative 5/3 meters per second, or if you want it as a decimal, that's about negative 1 2/3, or negative 1.67 meters per second. Okay, here's the solution as presented in the PowerPoint, and they got the same answer, negative 1.7 meters per second. Quick check 11:11. The two boxes are on a frictionless surface. They had been sitting together at rest, but an explosion between them has just pushed them apart. How fast is the 2-kilogram box going? All right, you can think about it. Pause it if you need to have a little time to think about it. But I'm pretty sure, so the momentum of this one will equal the momentum of this one, since the initial momentum was 0. So this one has a momentum, we might say, of negative 4. So this one should have a momentum of positive 4. And since the mass is 2, the velocity would have to be 2 to accomplish that. And that is the answer. Rocket or jet propulsion. The figure shows a rocket with a parcel of fuel on board. If we choose rocket plus gases to be the system, the burning and expulsion forces are both internal forces. The exhaust gases gain backward momentum as they are shot out of the back. The total momentum of the system remains zero. Therefore, the rocket gains forward momentum. So this is, again, very much like an explosion kind of model, where you have one system initially being the rocket and the fuel together as one thing. And then as it goes, the fuel is, the exhaust gases are coming out the bottom there. And so it's becoming not just one thing, but more than one thing. So it's, as it goes away, the momentum going away will equal the momentum going forward for the rocket. All right, the total momentum, P, is a vector sum of the momenta of the individual particles. Momentum is conserved only if each component of P is conserved. Okay, so here's a little mathematical description of that. Quick check 1112. A cart is rolling at 5 meters per second. A heavy lead weight is suspended by a thread beneath the cart. So there's the lead weight that is a part of the cart because it's suspended from the cart, so it's attached to the cart. Suddenly the thread breaks and the weight falls. Immediately afterward, the speed of the cart is what? You might want to pause it to think about it. You might be tempted to say, well, this thing has a momentum that needs to be conserved. So if it loses mass, then it needs to gain velocity in order to conserve its momentum. That might be so you might want to say C. But here's the thing. So when this little cord breaks and this lead weight is now a separate object, it's going to continue going 5 meters per second. The lead weight is going to go 5 meters per second just as well as the cart's going to continue to go 5 meters per second at first. The only thing that's going to stop it is when it hits the ground. Then it will no longer go 5 meters per second forward. And also gravity, as it brings it downward, is going to add acceleration downward, but it won't change the horizontal velocity of that lead weight. So because of that, it should just not even change the momentum, the horizontal momentum of this cart. You can also say, well, that's an internal thing, that there's no, and it's directed downward, not horizontally, so that is going to act independently of the horizontal momentum, because since it's a vector, vertical and horizontal are independent components. So in either direction, we should say it's still 5 meters per second. All right, back to rocket propulsion. Newton's second law, F equals ma, applies to objects whose mass does not change. That's an excellent assumption for balls and bicycles, but what about something like a rocket that loses a significant amount of mass as its fuel is burned? Yeah, so the fuel is a big part of the rocket. Like the space shuttle had, when it first takes off, it has these huge fuel tanks that it discards as the fuel is burned up. It discards them as it's up in the sky, and they come down and land in the ocean or something, and are recovered. And then the shuttle is by itself continuing on. It just needs those huge tanks of fuel to burn in order to break the gravitational force of the Earth to get to the escape velocity. And then once it gets into space, it doesn't need that quite as much anymore, so it can discard those fuel tanks. But that's a significant amount of mass it's discarding. So the fuel itself is a big part of the mass of the rocket system here. Problems of varying mass are solved with momentum rather than acceleration. So you might want to say that again. If the mass varies, then F equals ma is going to not be as helpful, because the mass, you need that to be a constant to figure out these things. But if the mass is varying, then momentum would be a better direction to go with your problem-solving strategy. As exhaust gases are shot out the back, the rocket, you could think of it like a gun, recoils in the opposite direction. So it's like the exhaust is the bullet, and the rocket is the gun. Figure shows a rocket being propelled by the thrust of burning fuel, but not influenced by gravity or drag. So, this is just going horizontally. So we're not taking in gravity or drag for this particular illustration. So you can think of the fuel as kind of one object. That's the model that it's showing right here. Like, think of the fuel as just another object. So the before state is a rocket of mass m, including all onboard fuel, moving with velocity v sub x, having initial momentum of that. During a small interval of time dt, the rocket burns a small mass of fuel and expels the resulting gases from the back of the rocket at an exhaust speed relative to the rocket. So you can see where they're going with this. They're starting to say, starting to get the dt in there. We're going toward a calculus kind of a thing. So, as the mass changes, it's not changing in a discrete way, it's changing in a continuous way, which probably means we're going to need to look at, things in a calculus way that has limits and things that can take those things into account to find, derivatives or integrals. After the gas has been ejected, both the rocket and the gas have momentum. Conservation of momentum tells us the mass of the rocket times the velocity of the rocket plus the mass of the fuel times the velocity of the fuel equals the initial and or final momentum of the system. The mass of this little packet of burned fuel is the mass lost by the rocket. So if it's a little infinitesimally small packet, if we're thinking of this as a continuous thing, then we would call that negative dm, like differential of mass. So a small, infinitesimally small amount of mass. Mathematically, the minus sign tells us that the mass of the burning fuel, the gases, and the rocket masses are changing in opposite directions. The gases are ejected toward the left at a speed v x relative to the rocket. The infinitesimal change in the rocket's velocity, we would call that dv. So, so if you kind of solve this equation, for dv, you would divide by the mass of the rocket, and you'd end up with the differential momentum v dm of the fuel divided by the mass of the rocket will give you the differential velocity of the rocket. Integrating the rocket's velocity between before and after, we find that the rocket's velocity when its mass has increased to m is, so you're doing this with respect to m, I think. So, the integral of a rational function, the integral of 1 over x is ln of x, which is where this ln is coming from. Initially, when m equals m naught, b equals 0, because ln of 1 equals 0, the maximum speed occurs when the fuel is completely gone, and m equals the mass of the rocket. This is the maximum velocity. So in other words, when the fuel has been burned completely, it has had its maximum acceleration, it has had its maximum amount of time for the acceleration to increase the velocity of the rocket, will equal this. So this may be a good equation to write down. What does it mean? It means the maximum velocity that rocket reaches at the end of its fuel burn will equal the velocity of the expelled gas, that's what VEX stands for, times the natural log of the mass of the rocket plus the mass of the fuel initially over the mass of the rocket again. So that would be, again, a good thing to write down. Here's an example. Sounding rockets are small rockets used to gather weather data and do atmospheric research. One of the more popular sounding rockets has been fairly small, 10 inches in diameter, 16 feet long, Black Brant 3. It is loaded with 210 kilograms of fuel, has a launch mass of 290 kilograms, and generates 49 kilonewtons of thrust for 9 seconds. What would be the maximum speed of a Black Brant 3 if launched from rest in deep space? So the reason they're saying deep space is so that we will know that we should not account for gravity affecting anything. All right, this seems like, okay, we're going to need this maximum velocity equation from the previous slide that we probably wrote down. What do we have? We know the mass of the fuel. We know the total mass of the rocket and fuel together. So if we just subtract the mass of the fuel from the total mass of them together, we can know the mass of the rocket. So we know all three of these, but we don't know the velocity of the expelling gas. We need to know that if we're going to know the maximum velocity that the rocket reaches. So how can we know that? So let me take you through a brain exercise to figure that out. So how much fuel do we have? We have 210 kilograms of fuel, and that whole thing is burned in 9 seconds. So divided by 9 seconds gives me 23.3 kilograms of fuel per second. All right, so that's the mass per second. We want to know the meters per second. So here's how you can do it. Since it gives us the force, 49 kilonewtons or 49,000 newtons. Force is kilograms times meters per second squared. If we divide that by kilograms per second, what does it leave us with? All right, let's analyze that. So I'm saying to divide the force, the thrust force, divide that by the rate of consumption of the fuel in kilograms per second. Kilograms times meters per second squared times, I'm just doing a keep change flip here, seconds over kilograms. Kilograms cancel. The seconds there cancel. So one of these seconds, and we're left with meters per second. So that is what we can do. We can divide the thrust by the rate of mass per second of the fuel. So that's going to be 49,000 divided by 23.3, and that will leave us with the velocity. This gives us the velocity, the escape velocity of those expelled gases. So 49,000 divided by 23.3, let me see. That is 2,100 meters per second. Now we have everything we need. This is going to be 2,100 times ln of the mass of the rocket, which is 290 minus 210, that's 80, plus the mass of the fuel, 210, over the mass of the rocket, which is 80. So do that calculation in your calculator, and you get 2,700 meters per second for the maximum velocity of the Black Brant 3 sounding rocket. If we assess it, it says an actual sounding rocket doesn't reach this speed because it's affected by both gravity and drag. Even so, the rocket's acceleration is so large that gravity plays a fairly minor role. A Black Brant 3 rocket launched into Earth's atmosphere achieves actually a maximum speed of 2,100 meters per second. And because it continues to coast upward long after the fuel is exhausted, reaches a maximum altitude of 175 kilometers, which is 105 miles high. That is the end. That's the last thing we have in Chapter 11 lecture slides. Here are the summary slides, if you want to review them, just to remind yourself of the concepts covered.